Hi there, this is Tiffany. Welcome back to CSE 545 Software Security. In this video, we will talk about format storing vulnerabilities. Format storing vulnerabilities is a different type of stack vulnerability. It is very different from Stack Overflow. I hope that from this video, you will have a good understanding about format storing vulnerabilities. And if you don't, if you have any questions, feel free to come to my office hour and ask me questions over there. I'll be very happy to help you with understanding format storing vulnerabilities. All right, let's start to roll. I will first start with a normal printf statement. Suppose that we have a C program. In the C program, we're going to call printf with this following format string and those following arguments. So we know that this printf statement will output number from 1 to 8, since the format string is %d, etc. And according to x86-4 calling convention, we know that for a statement like such, part of the argument will be stored in register, and the other part of the argument will be stored on stack. And particularly in this case, the first argument, which is the format string, its pointer will be stored in register RDI. And then followed by that, the second argument, which in this case is number 1, will be stored in register RSI. And then so on and so forth. For the seventh argument, which is 6, it's going to start to be stored on stack. And also for number 7, number 8, which is the 8th and 9th argument, they will also be storing on the stack. And in fact, if you look at the stack, which I take a screenshot over here, you will see that the bottom of the stack, which is where RSP is pointing to, will be saving value 6, 7, and 8. And these 3 are the 3 values that are for printf statement. Now I'm going to ask a question. What will happen if we delete this part? So we still keep the format string, but we will delete the rest of the arguments. And I will give some minute to think about it, and feel free to pause the video to think about this question. All right, actually, even if you remove those arguments, it will still print something. So the way that it works for printf is that it will first check the format string, and then according to the format string, those, like %d, those format, it will find the corresponding arguments that maps with this specific format, and then it will print according to the format specifier. So in this case, if we remove those parts, then it will still go to look at register RDI, RSI, RDX, so on and so forth, and those that are on stack. And this is very interesting. This means that if we can control the format string, we can actually get the value of registers and stack by the time that we call printf. So in this case, we will be able to leak the values from registers and stack. And now let's take a look at the stack. Since we know at this point that if we control the format string, we'll be able to get stack information. Let's take a look at the stack and see what will happen if we have a buffer over here. And then let's say that this buffer is actually controlled by input. So it's like this buffer is going to read from input. It is user controllable, or say attacker controllable. And then we're going to printf the buff. And also let's assume that right now, buff is the only local variable on the function. And then that means that actually RSP, which is the bottom of the stack, will point to the value of buff. So in this case, when we start to printf buff, we're going to go for 1, 2, 3, 4, 5, 6, 7. So starting from the 6, 7, 8, starting from the 6th argument, since buff is the first argument, starting from the 6th argument, the printf is going to look up on stack and get the value over there. In this case, the bottom of the stack is what we are storing for argument buff. So actually, we can control the value over here to let it print something that we want. And in this specific case, since we are storing %11x space, etc., we're actually print this as a hex, as an integer, a long integer in hex. This is the way that printf works, and this is the way that we can possibly control the content that we want to output. And now we have a question. The question here is, how are we going to control the buff, or say the input, the format string of printf, so that we can read the value that we want? And I'd like to give you a couple of minutes to think about this. Again, feel free to pause the video and think. All right, so here is the answer. If we want to have an arbitrary read, meaning that if we want to, read an address that we want to read and use the buff argument to output the value, what we could do is to put the address that we want to read inside the buff and then use the format %s, which is to print a string to output the value that this particular address is pointing to. So in this case, if we're making the 6th argument as %s, so we're no longer using %llx, which is to print the direct value. Instead, we're going to use %s. And in this case, the printf statement will still look at the stack, but here it's going to look at the stack's value as a pointer. And as long as we specify the value of the pointer in the buff, we will be able to get the value that this particular address points to. Since we need to put this in the buff, we just add this at the start of the buff because we want to make it as the bottom, right? In this case, the buff will have a prefix before the format string, which is the address of the arbitrary read. However, there is a problem if we just put the address over here. One is that when you convert this to little endianness, because elf is complied with little endianness. And another issue is that since we need to convert this to little endian, we will have to make sure that there is no 0 character over there. And actually, before I touch that, let me just emphasize what we can put over here and why arbitrary read is valuable for us. If you still remember previously, we mentioned that, stack may have defense mechanism, such as stack canary. And also, sometimes we want to leak the base address of the libc so that we can use rob chain. However, we don't know where the libc space is. And one way to look at that is to read the got entries value. So we need this arbitrary read for us to get a function pointer or to get a stack canary. And in this case, if there is a format string vulnerability over there, and the format string is controllable by us, we can use this format string to, do an arbitrary read and leak those information. Okay, so now let me just continue. with the issue that I just mentioned after we use little endianness, after we convert the pointer to little endianness. So here's the issue. Again, we're going to convert this to that. And because usually for x64 architecture, I mean, like the entire string is not going to be full of 64-bit. There will be some leftover at the start. So that's why if we convert this to a 64 little endianness byte sequence, you will find 0, 0 at the end of the converted byte. But we don't like it because if 0, 0, those characters happen happen in a string, then we do printf. The format string will stop over here. They will think that this is the end of the string. So we will no longer have this beautiful format string for us to do arbitrary read. Then what shall we do? So what we could do is that we're going to use positional argument in printf format string specification. For format specifier, you can specify the numbers of the argument that you want to put in format string. For example, if we have a printf statement again, and then in this case, we're going to use $2 or $1 to specify the index of the argument. So here you see that n is the first argument in terms of this format string, although it is the second argument for the entire printf statement. So I will just set over here is the first for the format string. And then m is the second for the format string. If we want to actually output n and m in a reverse order, meaning that we want to output m first, we can specify that this is the value that we want. And the way that we specify that is to use positional specifier, which is, like $2. Dollar is a fixed character, and 2 means that the position of m in this case is the second one for the format string. And similarly for n, since it is the first one for format string, we're going to put first 1 over here and then use this as $1. So now we have this nice functionality coming from printf, and we're going to use that to specify the argument that we want to read. Okay, so now let's go back to arbitrary read. In this case, now let's gonna actually move this part into the end of the string. In this case, even though the string is finished with 0, 0, it's not going to affect printf because printf will still start from the start of the format string and it's going to end over here, which is fine for us. And again, the %s is still going to point to the start. However, if we're going to have this %s point to the start, it will read this as a function pointer. And of course, it will trigger a segmentation fault because this is very likely to, this is very actually unlikely to point to anything. So it's very likely that you will get a segmentation fault. So right now what we're going to do is instead of let this %s points to the start of the stack, I want it to point to here, like some offset starting from the bottom of the stack. And the way that we look at that is we want to count those offsets over here. For printf, every argument is with a fixed length, which is 8 bytes. So now we need to construct the format string carefully so that this is what we want to read, and then we want to make this align with the argument, and we want to count the index of this argument inside the stack so that we'll be able to know that the numbers of the argument for the entire format string. And then we want to specify the index of this part by using the positional argument, like $ish thing, right? So now the question for us is how are we going to change this correctly so that we will use that to, correlate that to the specific address. Again, I'll give you a little time to think about this, and feel free to pause the video and think about this by yourself. And I want to notice that this is going to be very important because, for the future assignment, you will be asked to construct a buff, like construct a format string by yourself. So I highly encourage you to pause the video right now and then think about it so that you will be able to come up with the format string correctly by yourself. All right, so now let's work on this together. We want to put those first, so let's just consider to put those first. And after that, we know that we want to put the pointer. And after that, let's count the number of bytes that we have put on the stack and try to put some paddings over there in order to make sure that the pointer is aligned with this 8-byte requirement for printf. So here we have, this is 8-byte, this is 8-byte, 8-byte, 8-byte. However, over here, it's not going to be 8-byte anymore since there is, a little bit paddings that we need to put in order to make this part of the string also 8 bytes. Right now, we just put some values over there. It can be anything as long as the length of this is equal to 8 bytes. Okay, and after we have that, we're aligning the the pointer, and then we need to think about what is the value that we want to insert here for this positional argument. So we remember that the first 6 argument will be stored in register, and because the first argument is the format string itself, so starting from the second argument, which is the first one for the format string, is going to be stored in the register. So here, this one is actually the 6th argument for format string, which is the 7th argument for printf. Okay, so if this is the 6th, then 7, 8, 9, 10, 11. So now we know that this is going to be the 11th argument for the format string. So we need to put here 11. And I want to make sure that you notice that actually sometime if you put 11 over here, you will realize that this part of the string is no longer aligned because maybe originally there's no this 2 additional bytes inserted. So you want to do a second time adjustment so that after you inserting additional position argument over here, the entire format string, the entire argument of the stack is still aligned with the format string. So in this case, I put 11 over here, and I just put a decent amount of A's as the padding, and I can make sure that the rest of the pointer is still aligned with the 8-byte requirement. All right, so now we know how to do an arbitrary read using format string vulnerability. Next, what we're going to do is to do an arbitrary write using format string vulnerability. So you may wonder how that could happen, right? Because printf, it will only just print something. Why can't we actually write something instead of only read? Turns out that for printf, it has a very nice format specifier that we could leverage, which is %n. So before I talk about %n, actually I would like to try this by yourself. If you could pause this video and copy paste these lines into a C program and try what will happen. And you'll be able to get the output by yourself. And also, if you already know what %n means, you don't have to do that. And you can just use your brain to simulate the execution of the program and then think about what is the output. So the output here is gonna be 5. And why is that? This is because when we do printf hello and then followed by %n, %n will write the number of printed bytes into variable n. So here, %n is the argument that we specify in the format string. And this will also look into a pointer, which in this case, if you look at the screenshot over here, it's going to be stored in register RDI. So this is the address of integer n. And in this case, it's going to put the number of printed bytes into variable n. And before we are dealing with %n, we have printed hello, so that's 5 characters. So in this case, n will be equal to 5 after printf statement. And that's why in the next printf statement, when it outputs the value of n, you'll be able to see that n is equal to 5. And you will be able to see this string. And also, new line, of course, because the end of the format string has this new line character. This means that if we can control the format string, we can change the value over here so that we can change the value that's gonna be put onto variable n. So say if we're not saying hello, if we want to, make n is equal to 10, we can then just put 10 characters over here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we just put 10 A's over here, n will be equal to 10. So in this way, we can decide the value of n. So we can write any value that we want to variable n. However, that's not the end of the game. We still want to be able to not only write to, n with an arbitrary value, we also want to be more powerfully write to anywhere that we want. And this is going to be very helpful as an attacker, or say this is going to be very malicious, because in that case, we will be able to say overwrite the saved RIP, or say overwrite a function pointer with arbitrary value controlled by the format string. And I'd like to have you think about this by yourself. How are you going to use the controllable format string to write an arbitrary value to an arbitrary place? I will give you some hints first. Suppose that we have a buff as follows: hello %n, and then \n, and then we're going to use printf. And here there is a vulnerability. It specifies this is a format string vulnerability because we don't specify anything, and the format string is controllable. Okay, so in this case, what will happen? As we already know, %n will write the value of printed bytes, the number of printed bytes, to the second argument. And in this case, even though we don't specify the second argument, we know that the second argument should be responded with register RSI. So in this case, what will happen is that we'll actually write number 5 to the place that RSI is pointing to. And make sure that you understand that right here, it's not going to copy paste the 5 to register RSI, but instead it will write to the place that RSI points to. And this is because that if we extend this, which is the program will do when it parses this, it's going to have buff, and then the next is going to be the address of some place, right? And this is the same to what we have shown before. It's over here. It can also work on this slide as well, right? So we show here that the second argument will be the address of a specific place. So similarly here, although the second argument is not specified, it will still go to look at register RSI and then try to consider that as, an address, as a reference. So that's why in this case, we're going to write value 5 to where RSI points to. Cool. So now let's extend the format string. Let's extend it with more %n. So in this case, we're going to write more things onto those registers and as well as stack. So in this case, it will continue write 5 to those registers, like register that RSI points to RDX, RCX, so on and so forth. However, for the last one, it will start to write values on stack. And this is fantastic because this is exactly that we want. In this case, we can start to overwrite values on stack. And in this case, again, because this printf, according to the calling convention, when it starts to write values on stack, it will start with the bottom of the stack. So in this case, it will read the value over here on stack, right? And the same as what it does for the other, register or say the other argument, it will reference this part. So if this part is referenceable, means that if it is a pointer that's put over here, then it will dereference this pointer and then put the value f to that place. So now I'm showing over here. Suppose that we want to write an arbitrary value to a place, an arbitrary place, but in this case, let's suppose that place is, this particular address. Then what we could do is that we just put this address at the start of the buffer, which will also be the bottom of the stack. So in this case, once we do write, the last argument, this, will be corresponded with this particular pointer, and then this pointer will be assigned with value 5. And now you may find an issue over here. When we write 5 to those values, we actually don't know the value of RSI, RDX, so on and so forth, those registers. So what if when we dereference RSI or RDX, there is actually not dereferenceable? So it will trigger segmentation fault. So how can we avoid this? Avoiding this actually is pretty easy. All you need to do is to change from %n to something else. So you can just make it as %x. Those %x will just print the value from RSI, RDX, since they are corresponding with each other. And then for the next one, which is the last one, %n, I will go to the values on stack. Besides register dereference issue, we may come across another problem. Suppose the goal for us is to overwrite this address with the value of 1,000. And previously we have said that, if we want to make this equal to 1,000, we have to make sure that the number of bytes that are written before we have this value has to be equal to 1,000 bytes. However, in this case, we just don't have that much value. And you may want to, like maybe putting 1,000 A's over here, but that's going to be too long, and maybe the buff will not be allowed for us to put tons of characters. So the question is, how are we going to make this number exactly equal to 1,000? Turns out that we can control the number of outputted bytes using format specifiers. For example, suppose that we have an argument x with the value of 10, and then we're going to output this variable using a format string of %010LD. You may feel this very confusing, but you can actually separate them in different parts. And for format specifiers, it can compose of 1, 2, 3, 4, 5, 6 different components. In this case, we are using 4 components. The first one is the flag, and then the second one is the minimum width. So these 2 parts specifies that if the outputted variable is not as long as 10 bytes, then we're going to pad the outputting result with 0. And then here L, pay attention, this is L, not 1. And L means that the variable that we want to output is a long, which is corresponding to the type of variable X. And then the last one, D, this is called conversion specifier, and this is the most common one that we come across for printf statement, which specify the format. Like D means that this is decimal. We can also just use X, which means that this is going to be in hex. So in this case, we can print X as a long int with the minimum length of 10 bytes. And if it's not, we're going to padding that with 0. Here, X, we know that the value of it is going to be 10, right? So if we just do printf, we know that it's not going to be as long as 10 bytes. The output is going to be 8 zeros before 10, which is 1, 0, and another 2 bytes of the printed string. So in this case, we can use a format string to nicely control the number of outputted bytes. Now let's come back to the original goal. So recall that we want to make this specific address equal to 1,000. Instead of putting a lot of paddings and then make this part of the output bytes equal to 1,000, we're going to use format specifiers to output the correct number of bytes before we put the value 1,000 into the address. We are going to specify each of the output, which is 1, 2, 3, 4, 5 parts of the output. Each of them, we're going to give them 20 bytes. And we specify it by 0 to 00x. So this means that for whatever value that is going to output according to this format string, it's going to output in 200 bytes. And if it's not as long as 200 bytes, we're going to pad it with a 0. And similarly for the others, it's also going to output with 200 bytes. So in this case, we're going to have 200 times 5. So we're going to have 1,000 bytes before we write the number of printed bytes into %n, which is specified over here for the address. After we are able to control the written value with a relatively shorter length of buff, the next problem for us is that, similar to what we have come across for arbitrary read, when we convert the address to little endianness, there's going to be a break because of the 0 over there. So again, because of 00 bytes, it's going to break the format string. So what we're going to do, similar to what we did for arbitrary read, is that we are going to put this specific address at the end of the format string. And then we need to recalculate the part on the stack so that we can get the numbers of the argument, the positional argument, correct. The way that I usually work on this is that I will first put the address in the end, and then I'm gonna simulate the stack and check how many bytes that I already put onto the bottom of the stack. If buff is in the end of the stack, then I would just put, the existing format string over here, and then calculate the number of bytes over here that I already put, as well as the position of this pointer that I put over here. Let's just sort it out, organize it. And for each line, I'm going to put 8 bytes because I want to make sure that the pointer that I put in the end is aligned with 8 bytes. So in this case, I have 1 argument, 2, 3, 4. And after that, there is some paddings that I have put over here so that I can make this as another argument. And followed by that, it's going to be this one. So it's 1, 2, 3, 4, 5, 6. This is going to be the 6th argument in stack. And remember that before that, we already have 5 arguments storing in register. So for format string, this is going to be the 6th one. So this is 6, 7, 8, 9, 10, 11. Now we know that the pointer is going to be the 11th argument. That's why I put 11 over here. And also I want to put 11 over here as well. And in the end, I'm going to put some padding over here. So I'm just put this part as the padding, which will make sure that before the pointer, there will be a decent number of bytes, which is a number that can be divided by 8. Okay, so now we have a perfect format string. Now we already know how to take advantage of format string vulnerability and how to launch an attack that is able to do arbitrary read and arbitrary write. So next, let's talk about how to defend such kind of vulnerability and how to avoid that, since we're going to write secure code in the future. Turns out that defending or avoiding format string vulnerabilities is relatively easier than attacking it. All you need to do is to make sure that user cannot provide format string. Next time, if we're going to print something, and also if that is related to user's input, make sure that you have a nice format string specifier instead of just print it directly. You don't want to have a statement just like printf buff. But instead, you always want to make sure that you have provided the format string so that buff will not become the format string for a statement such as printf. Okay, that's pretty much the content that I hoped to know for format string vulnerabilities. If you have any questions, please come to the office hour and ask me. In our next class lab, we're going to work on format string vulnerabilities together and attack of format string vulnerabilities. They're going to host it in the server. I will see you in the lab class. Bye.